All right, so we have introduced Monte Carlo to you, at least in theory, and now we want to look at the actual software itself and how it works. So by now, I'm assuming that at least most of you have managed to install the software, and you should have desktop icons with at least BeamNRC, DOS XYZ, and BeamDP, and EGS GUI as well. These other two, EGS View and EGS INPRZ, we are not going to use them for this course. So, depending on where you stored your EGS home, I know maybe some of you have stored them in different directories, but basically, for you to model a linear accelerator, you need three basic things, right? You need an input file, you need a module or a spec module. If you remember, I did mention that they are what we call component modules, right? Which model each and every component of the radiation unit. So you need a spec module that specifies the components. You need an input file. Input file describes the geometry of the linear accelerator. With all the materials and the compositions and the dimensions. And you also need the pegs data, which is the cross-sectional data that contains all those interaction probabilities. All right. So if you open your let me just begin by opening the graphical user interfaces themselves. Then I'll show you the contents of the folders and where you can find the respective files. So let's say we want to model a linear accelerator, right? What I'll do here is I'll open the example files that have already been that are default, so they come with the software itself. And I will just open those and we will do a few tweaks and see how it goes. All right. So you have opened your BeamNRC graphical user interface. It looks like this. You have got file, preview, execute. So what you do initially, I'll tell you a shortcut. All right. But let me begin with the longer process, because the shortcut might not work if you have not titled your files appropriately, but hopefully not, because it's quite simple. But let me start with a little bit longer process of loading my linear accelerator, because my linear accelerator, like I said, is already part of the installation. It's there. So I'm going to load it. So you go to File, right? You load a previous accelerator, right? Don't specify a new, because you specify a new accelerator if you're starting from scratch, right? If you're starting from scratch, if you do have the geometry, the dimensions of the Linux, then you can start from scratch and specify and start, entering in or inputting all the information needed to create an accelerator. But we already have got one, so let's load it, right? I'm going to start with the 16 MVP. This is a photon beam, 16 MV photon beam. Right, so I'm going to double click on that. Okay, this is a module, so you only click once. So this is a spec module or the component module file. All right, so this file contains the names of the component modules that are used to model each of the Linux components. All right, so for example, remember I showed you earlier on. Let me just show you representationally. So you see what I'm really loading from here. Let me see. All right. So what I'm loading right now are these things on the right. All right. For example, if I'm loading this particular Linux, I'm loading the slabs, constant, flat fill. These are the component modules. They are contained in this file that is .module, right? These are the component modules. You load it, right? Okay. And then you get a pop-up window. So now you see I have loaded it. Now I've got all the component modules, right? on the left, you do have the names of each component module. And then in the middle here, what you have is the user names that you put, like if you wanna model a target, for example, right? You use the slabs component module. If you wanna model a primary collimator, you use this. So these are the names that you as a user actually give to have got like an intuition of which component is being modeled by which component module. Right. So now you have got your components loaded. Now a pop-up comes up automatically here. This is to sort of load the cross-sectional data that I said. It's called the PEGS4, right? The PEGS4 file contains the cross-sectional data, and you browse a hen house, all right? You see that sometimes if you want to browse local area, it might give you issues, but as you can see, there's only the 521 ICRIU. The 700 ICRIU is not there. So browse the hen house, and you might need sometimes to browse the local area if you have created your own PEGS4 data. All right, so for those materials that are not default, that don't come with the software, the materials that you create with this EGS GUI, right? I told you I'm gonna show you a little bit about this, but this basically creates sort of a customized material. So let's say you want to model DOS in the presence of a material, a foreign material in a patient, like an implant, right? You can generate the cross-sectional data of the implant here. Once you output it, it's mostly going to be output into the local area, not in here now. So when you're browsing, you can see where your PEGS4 data has been outputted. But now we're just using the default. So let's go to henhouse. We use this 700 ICRIU. Okay. Now we have loaded what? Our PEGS4, right? Which is the cross-sectional data, and we have loaded our component modules. Now we need to load our input file, right? So those first two, they are loaded at the same time, right? I'm talking about the PEGS4 and the component modules, right? Now we input the input file separately, all right? Now we're loading what? Previous input file, right? Remember I said we want to model the 16 MVP. This is actually a folder, right? Each and every radiation unit is got an input file which is stored in a folder, right? And I'll show you the way this folder is named, all right? But you double click, and then you click on the EGS input, EGSINP, which is input file. Okay, now we have loaded everything. Okay, we have loaded the accelerator. We have loaded the parameters, which are the top line here. Accelerator MVP loaded represents the components. Accelerator parameters represents the input file, and then PEGS4 file represents the cross-sectional data. Now we've got all three loaded. Now, once you have done that, you can compile just to see if everything is okay, if there are no errors, right? But sometimes you might see an error, which is just a bug. Normally when you compile initially, for the first time, you might get an error. I might not, because I have already compiled this before, all right? So compilation successfully. If for those of you who have got a working EGSnrc, you can try this with me right now. You can just open the same way I've done it. But if you haven't, it's okay. I'll show you the shortcut to open all these three files. So you build and compile. If you get a compilation failed message, then just do it again. Okay, so let's say you compile and you get a failed here. You just say okay, and you do it again. Normally the second time you get a compilation successful. Right? You shouldn't get any error, because this is a default file, so it shouldn't contain any errors. However, if you create your own accelerator, it's possible that you might get an actual error, which is not a bug. But okay, once you've compiled, you can close it, and then you can run it. But before you run it, maybe you can check if you go and edit input parameters, because since this is an illustration, I don't want to run a simulation that's going to take 30 minutes to run. So I'm going to go on in edit main parameters here. And what I'm going to change is the number of histories. Remember, I said histories determine the accuracy. Okay, I think this is fine. This is 15,000 histories. So this should run in a few seconds. All right. Everything else you can leave it as it is. You can play with the histories. So let's stick to 15,000 and then run. We've already compiled. Now we run it. All right. So you go on execute. All right. And by the way, it splits your histories into 10 batches. So for 15,000, so now you get job is finished, right? So you say, okay. So like I said, the simulation is split into 10 batches. So since our histories were 15,000 each case, so J case represents the number of histories run for each batch, right? So it's 1,500 for each times 10 batches. And of course, you get some simulation summary, elapsed time. So this simulation took about 7 seconds. And it gives you the number of histories run, or the number of histories per hour, right? So you can use this to see how many hours are going to take if you increase your histories. But I wouldn't trust that calculation because we have simply run too little histories for us to rely on this data. So I would recommend, let's say you use a little bit more histories, and then you can sort of work out how much time it's going to take if you, let's say, double your histories or triple your histories. All right. Some of the things you learn as you go. So now after executing or running the simulation, right? You have done your beam analysis simulation. But now we want to look at the output, all right? So now let's go to EGSwarm and look at the output. Of course, you can do this on a terminal shell or a command prompt. You can list all the files by typing, first going into the directory, right? CD, change directory, then you go into the working directory, which in this case, we are modeling the 16 MVP Linux, right? So if you, for example, open a terminal here, right? So what you can do is you can simply open the folder and then you open it here. So it means your terminal is already in that working directory, right? So you don't have to say CD or change directory. And of course, you can list the files in that folder, right? Or you can list with attributes. I believe you put an LA, if I'm not mistaken. So it gives you the file and all the information or the properties for each file. But it's kind of messy. But for those of you who prefer this kind of thing, you can do that. I prefer the simple way of just going back and forth. So sometimes the terminal is better if you are doing parallel processing. And I'll talk about parallel processing a little bit later, which is when you want to break down your simulation into several simulations and then you can combine the output. But anyways, we have run our simulation for this accelerator, right? And we've opened it, and we should see an output phase space file, right? This is the output. Don't try to open it. You're not going to see anything that makes sense to you. But basically, it contains our beam, all right? In this case, our beam has been, or let me say our phase space has been scored beneath the collimators. All right, so we are collecting the beam, just after it's been collimated. All right, so this is the output phase space that's going to be used or transported to DOS XYZ for patient or phantom simulation. But let me just preview the accelerator just to show you what it looks like, right? So you can go on preview and you can go on preview accelerator, okay? So this will give you all the components of the accelerator, right? At the top here, you've got your X-ray target, right? Remember, we are modeling, this is a 16 MVP photon beam. So we do need a target, primary collimator, flattening filter. This is an ion chamber that is used for dose monitoring, basically. There is a mirror here. If you can see, there's something slanted. It's usually at 45 degrees. The purpose of the mirror is to give you a light field. So there's a source of light somewhere within the linear accelerator, right? And the linear is directed towards the mirror. And then the mirror directs the light towards the collimators. And then the light is going to show on the surface of the phantom. So it's used for visualization of the field. All right, so that's what we call the light field. All right, so it takes the shape of the field itself, of the radiation beam. All right, so that's the purpose of the mirror. You might not see it clearly from your side, but it's there. So some simulations you may ignore it. If you like, it really does not attenuate much of the beam. But if you want a perfect or a more accurate representation of the geometry and components, you can include it, right? So it's modeled by the mirror, right? That's the mirror component. And then you get to the jaws. Jaws is basically the collimation system. And I'm not sure why there's a slab at the end here. It's probably the exit window of the beam. It's probably the exit window. But so this is the preview of the accelerator that is built in, or let me say that comes with the installation. All right, so when you install your BeamNRC or your whole EGS package and go into the EGS home, right? So EGS home, well, so the location of this would be different for each and everyone, depending with where you chose to save or where you chose to locate your working directory. So you just go to your EGS home, wherever it's located, and you will see there is a 10 MV or MEV. This is an electron simulation. Then there is 16 MVP. This is a photon simulation. So these come with your installation. And also this beam phantom, I have never looked at this one, so I'm not sure exactly what it simulates. All right. Beam slabs just consist of a target, a block of material. It's not a full linear accelerator, right? Some of these other files, these are my personal files, but as you can see, the where you name these is, you see there is a beam, right? Capital letter underscore, and then the name of the input file. So if you open this, you see there's x phantom dot blah blah blah, x phantom dot blah blah blah. All right. So that x phantom is what is what you join to the beam underscore. All right. Why is this important? Is because if you want to use the shortcut method, which I'm going to show you, then you're gonna have to name your linear accelerator using this kind of nomenclature. But let me show you how you can load all those files using the shortcut. Okay, the other method I showed you was kind of, but before I do that, okay, I just want to show you the location of the 3 files that I loaded earlier on. I did load the input file, I loaded the spec module, right, the .module file, and then I loaded the pegs4 data. All right, so The input file itself is within the EGS home, and then you go to the Linux file, right? So the 16 MVP is the one we did. So you look for the EGS INP, right? This is the EGS input file. So that's the input file. It's within the Linux folder itself, right? And if you want to look at the spec modules, right, or the module file that contains the names of each and every component, then you go to beam NRC here, and then you open the spec modules, right? This is the module file for that linear accelerator that we just saw. It's a simple file. It only consists of the names of the spec modules, all right? So it has got component module names, right? In other words, the inbuilt subroutines that model each and every component. And then identifiers, right? So these are the user names that you put. So if you're modeling a target, you just say target. If you're modeling primary colorimeter, you are free to use whatever where a word is intuitive to you. So this is the module file. It's only a 2-line file. Even if you open this one, this is for electrons, right? Component modules and the identifiers. Right? And this is true for all the other radiation units. In terms of the PEGs 4, PEGs 4, you can try, if my memory serves me well, it should be in Henhouse. All right, so you go to EGSnrc, all right, Henhouse. Actually, the PEX 4 file is in 2 locations, right? Remember when I was loading you, remember when I was showing you, there was the local area, and then there was the Henhouse, all right? So if you go in Henhouse, right, Henhouse is located in EGSnrc. Remember, there's 2 major folders. I hope you can see both of these. Please confirm in the chat for those of you who have installed. Please confirm that you have got the EGS home and EGSnrc. Just type yes or okay in the chat, so I'm sure we are on the same page. So that, all right. So the EGS home is the one that I was showing you. It consists of the folders with each and every machine, right? Now we are going to the EGSnrc to open. I just want to show you the location of the PEGs 4 data, right? You go to Henhouse, and then you open PEGs 4. Where is it? Yeah, here. All right. And then you open the data. Okay. So you've got the 521 ICRU, 700 ICRU, right? So these are default. They come with the software. You can append sort of, if you create your own custom materials, you can append them to this file. So you can do that on the EGS GUI, like I said. So you can go on PEGs data. This is something I think I'll show you next time. I don't want to overload you for now. We simply don't need to do this now. But let's say you have input all the parameters you want for your custom material. Then you can then append. You see, there's an append to existing file here. So after you input all the data, you can append and then put the existing file. I think you'll be asked to browse for the existing file. Then so you can append to any of these 2, the default ones. All right. So that when you simulate, BeamNRC is not gonna say you have got missing cross-sectional data or material in your PEGs 4. All right, so this is one location with PEGs 4 data. There is another location, I believe it's in Eggs Home, but let me just do a control find. I'm not sure exactly where it is. Right, so PEGs 4. All right. So I'm depending with if you have updated your Linux, it should show you the path right on top. So if you're not sure where something is located, you can simply say Control F and then you type its name and then you open it. Once you open it, if it's a folder, you're gonna see the path. So in my case, it's home desktop, EGS home, PEX4 file. So that's the location of the other PEX4. The one, if I may show you here, let me just show you. When I load my accelerator, all right. Remember, I showed you that now when you are scanning your PEX4, there are two locations, right? I showed you the hen house, right? And there is also the local area. The local area only has got one in my case. I'm not sure if you guys have got two in your installation, but it should be the same. All right. So this one with one PEX4 data is this one. But like I said, use the one in your hen house. Unless you want to create some new materials and I've appended them to this file. But anyways, I hope it's making sense. Now, what I'm going to show you is how to load your accelerator using a quick method, right? And this method works if you have titled your folders correctly, okay? Now, you go to File, and then you simply go directly to Load Previous Input File, right? We are simulating the 16 MPP. Click on it. Okay. Oh, I think it's because I have got this thing open. Let me just close everything. And then we open EGSnrc. All right, so File, Load. Okay, click on it. Okay. Browse in-house. Then, all right, it's loaded. So you see, in this case, you have only done it in a single step. Okay, you don't have to load the spec modules manually. All right. So if you have got your files titled correctly, the moment you load your accelerator, the software is going to automatically look for component module file that corresponds exactly with your input file. So you won't have to load your spec module manually. All right. You simply go to load input file, and then you load it, and then you simply have to click on your PEX4 data, and everything is loaded. And of course, you can do preview accelerator, compile accelerator, right? And you can do run accelerator, right? Run or execute, and then it does the same thing I showed you earlier on. So that would be your beam NRC simulation. All right. And in terms of the actual geometry of the linear accelerator itself, all right. So in this case, of course, we are working with an example, right, or a Linux that has already been created, right? Let's say you want to create your own, but you've got all the data you need. So you've got all the dimensions and geometries, right? So I'm gonna do it for one example. I'm just gonna model a slabs or a target only, right? A simple block, right? So what you do is File, and then you specify a new accelerator, okay? Now, to model a target, which is simply a block, you need slabs, right? This is the component module that is used, right? And by the way, I think in my, I did give a list of component modules that are used to model different components. So for a brem salon target, you can simply use slabs. Primary collimator, you can use Constack. You can also use flat field. It's very intuitive, as long as you do have adequate information or data. So for this illustration, I'm just going to show you with a slabs, right? I'm just going to model a simple block here just to show you how it's done. So slabs, you click on it, you click this arrow, it should, this is the name of the component module, right? You can't change it. The identifier is the title of whatever you are modeling, right? In this case, I'm modeling an X-ray target, right? So I can do that. Let's simply say X-ray target, and then you click on add. Oh, I see. You cannot actually put spaces, all right? So I'm just gonna say X-ray target as one word, or I can just say Brem salon target, or let me just call it target. All right, so make sure you. I think you can put an underscore. Let me just try that. I'm not sure. Or X target like this. All right, that works. So an underscore works. Just don't put spaces. Okay. Okay, save and close. All right. Now you are asked to give the name of the module. All right. So what I'm modeling here is an illustration. Okay, I'll just say, okay, let me just call it target, just to give it a more intuitive name. So let me just say target example. All right, target exam. All right. So now we are creating that module file, right? Okay. Now we want to browse the cross-sectional information, right? Let's browse in-house and we input 700 ICRIU. All right. So now we have we have loaded, or we've created the accelerator, which is the spec module, and we've loaded our pegs. For what we don't have is the input file. Now the input file is what you get after saving. But of course, you're gonna have to edit these parameters to define the geometry of your target. Okay, so since this is an illustration, we might have some errors because it might need a bit more scrutiny, but hopefully not. I'll leave everything else as default. I'm just gonna give it a title. So I clicked on these are the main parameters, okay? Where you specify things like number of histories, cutoff energies, and the type of source, right? So let me give it a title and just say X ray target block. Here you can put spaces, it doesn't matter. All right. The medium, if you click on it, you're gonna get a bunch of mediums. So these mediums are in the pegs for file, right? That I loaded. So medium, let's say we want to model this is the surrounding medium. By the way, if you are not sure about what you are looking at, you can click on the arrow, right? It's going to show you, it's going to give you a brief description, right? So I'm just thinking of putting air here, right? This is the medium which is surrounding that component module. So in a realistic situation, that would be air. So I'm going to select air. Where is it? Air 700 ICRIU. All right. I'm going to leave everything as it is here, right? And I'm just going to change the number of histories, and I'm just going to increase them a little bit. Maybe 1,500 or 15,000. That's fine. Another thing which you must change is the number of CPU hours allowed, because if you leave it as 0.99 hours, the moment it gets to 0.99 hours, it's going to terminate your simulation. So I would encourage maybe you put 100 or even 500, okay, just to make sure. But I don't think anyone's going to run a simulation that long. But anyway, just put a large number. 500 is a good number. Brainstorming splitting, this is a variance reduction technique. I'm going to leave it as none. I'm going to leave everything as none. Now I'm going to define my incident particle. and the type of source, right? Remember, I'm simply modeling the XY target. So I'm simply modeling Bremse style of production in a target. No collimation, no flattening of the beam, nothing, none of that. I'm simply modeling the initial part of the linac, right? In other words, I'm modeling this part here. I'm modeling this part only. I'm not going to model collimation or flattening or whatever. Right. So I'm going to choose my incident particle is obviously an electron, right? This is the particle that is incident onto the source. All right. What type of source are we dealing with here? Let's just make it a simple beam, parallel beam from the front. Okay. So I've got an electron beam that comes perpendicularly onto the target. Okay. So I selected source number 0, which is just a parallel electron beam that is impinging onto the target perpendicularly. Right. Beam radius 0, 0.1. Let's just use 0, 0.1. If I ask you to do this, I'll give you all the information. Okay, like this is the beam's size. All right. Incident direction cosine. All right. So now you are taking the cosine of the X, Y, and Z plane. Our beam is coming perpendicularly, right? So cos x-axis, right, which is perpendicular to the beam direction, right? So basically it's cos 90, right? Cos 90 is 1, is it? I'm forgetting my mathematics now. Is it 0 or 1? It's 0, right? Okay, so 0. With the y-axis is also perpendicular to it, so again 0. With the z-axis is in the same direction, so it's basically cos 0. All right, it's perpendicular to the z-axis. So the beam is as a cosine of cos 0, which is 1. All right. So we have defined the direction of our beam and the radius of the beam. Let's give it an energy. Let's say 6 MeV electron beam. You can also select a spectrum if your beam is not a purely monoenergetic beam. If you've got a spectrum file, you can do that, but we won't do that for this course. Unless you are doing research, then yes, a spectrum would be a bit more accurate. All right. So we have defined the source, right? In terms of the E-cut, usually they'll give you recommendations, but this is basically the energy below which the particle is no longer tracked. So if the particle gets to that energy, it's no longer tracked, right? And E-cut of 0.7 MeV is generally used. So we are going to use the default, okay? In terms of P-cut, okay, so E-cut is an electron cut-off energy. P-cut is the counterpart for photons, okay? So if you're not sure, click the question mark. Usually a P-cut of 0.01 MeV here is generally used. So we are going to use 0.01 MeV. All right. We are not gonna use any range rejection, which is also part of variance reduction. No photon forcing. Scoring planes. Let's just say 1. We are scoring our dose at 1 point, right, which is just beneath the target. Right. So I think it gives you a maximum of 3 dose or phase space scoring planes. Right. So if you model, let's say, several components, you can score your dose at any point, but for a maximum of 3 scoring planes. Okay, so we just want 1, right? Where exactly it's gonna give you a pop-up. So where do you want to record your output? We just have 1 component module, right? So if you had 3 component modules and you want to score below the 3rd one, you simply put 3. In this case, we've got 1 component module, so we'll just put below that. Zone type, let's just make it a square, right? And scoring zones, let's just put 1, right? What is the half width? I'll just give it a large number, all right? 10 is good enough, right? All right. So we have defined our beam, okay? In terms of the material of the slab itself, right? So now we have added our input parameters, right? So we have defined the surrounding medium, which is air, number of history is 15,000, maximum time allowed, we've given it 500, and we've put in the cut-off energies and the scoring plane being below the slabs, and we've defined our source to be a 0.1 millimeter diameter beam that is perpendicularly incident onto a target. So that's what we have done. What we have not done is to define the material of the slab itself, right? Of the target. So now we can give it a title, right? Let's just say X-ray target. Okay. It doesn't have to be that accurate. It's just for your own just for someone maybe who views your simulation to see what they are looking at. So it's an X-ray target. Half width of outer square boundary. This is basically the width of your component module. Our target, you can give it any width really, but let's just give it 10, right? Just so that it can cover the whole beam. But we know our beam is only 0.1 centimeters wide or in radius, okay? So distance of front of material to, this is one thing that I want to let you know, that for the first component module, right? This is the distance from the front of the first non-air material to Z is equals to 0, all right? What you can do is you can just put a small number like 0.1 is a good number here, all right? It's basically the distance from the surface of the target to the source. It's technically 0, but EGSnrc doesn't like that. So just put 0.1, okay? Number of slabs, it's simply 1 block, right? Layers, we don't have many layers, it's just 1 layer, so we're not gonna, the thickness of the slab, I'm just gonna give it a number, let's say 0.3, right? Like I said, this information is available for every machine, all right? So the thickness of that block is 0.3 centimeters. You should, and you should know that the units are in centimeters, right? Cutoff energies, we are not going to change it. These are the same numbers that we put in the main parameters here, right? So don't change them. DOS zone, all right? You can indicate whether you want to score the DOS in this or not, right? Yes, we want to, so we can just put 1, but if you don't want to score, then you can put 0. Latch bit, this is not very important for this illustration. So I think we can just put 0 here. All right. And then the E-serve is basically the maximum energy that a particle can have for range rejection to be considered. All right. And its default value is set in the main inputs. So I believe here, if I just want to go with the default, let me quickly check here. It's used to minimize errors due to assumption that its default value is the ESEF global. Okay. Let's just put 0. Okay. Let's just put 0 so that we know the range rejection is considered. Okay. 0 is safe. We don't want to reject particles that still have got sufficient energy to contribute to those. So what is the material of the target usually? It's tungsten, right? So let's go to tungsten, which is normally W700. So that's the tungsten target. Okay. You can preview. Okay. So this is just a block, remember, of material. And this gap here, this is the 0.1 distance that I put here. Remember, I said beam NRC doesn't really like 0, but we can try it out. If I put 0, I believe it's simply gonna give us a solid blue, okay? But I'm not sure if this is going to run, but let's leave it at 0 and see what happens. If it doesn't work, then we'll put 0.1, in which case it's going to give this gap, which is air. That is why you've got two different colors. So the colors represents the medium or the media. So this is air and this is tungsten slab, all right? But let's keep it at 0 for now. Let's see. Now let's save our input parameters, all right? Save input parameters. Hold on. Okay, let's load previous input file. All right. So since this is our first time, all right, remember we are generating a new accelerator. So initially you load a previous input file, even though there is no such input file. Let's try to see if we can come up with a good name here. Maybe we can title it target. What was the name I used for the spec modules? I believe it was X target. But let's see. Let's just say X target. Right. Let's see. Whoa, I don't want to discard this. Cancel. Oh yeah, no, my bad. I'm actually supposed to click on save input parameters as, okay? Okay, we are not loading any input file here. We are not doing that. We are creating a new input file, but we want to save as because it's the first time. So we want to give it a name. Okay, so once you do that, it's going to say that directory does not exist. By the directory that talking about here are these folders. So we are creating this now. All right, we are creating this. So now it says created. Yes. All right. So I just want to see, okay, the current directory is EGS home. We are in Beam, okay? So this is the directory we are in. So let's give it an input file. Let's just give it the same name, okay? Just target exam, same input file name. You can give it a different name, it's okay. Target exam. All right. You have an input, a title, and the charge of the source, okay? And source type. Okay, so those are the things I haven't put. The title, okay? You can put whatever you want. Okay, I'm just gonna put rubbish. What else? I'm not sure why it removed these things that we defined. But anyway, it's probably because I tried to load something else. So I'm just gonna quickly do this again. All right, so everything is there already. Okay. And I'm just gonna input this again. It probably deleted it when I tried to load another input file. All right, and let's see if everything else is fine. Number of scoring planes, I said it's 1, and I said it's 1, and I said it's a circular region, 1 zone. Hold on. This is the half width. I'm just gonna say 10. So I think everything is set. Let's see if we can compile and run. Let me first save everything I've done. And then I'll try to compile, okay? and compiling, it might say error initially. And then, like I told you, you just have to build it again. So now it's going to say there's no make file. It's going to rebuild. So it's going to create all the files that are needed for you to run the simulation. Okay. So you just say, okay. Okay. In this case, it has said successfully built. Let's see if it's not going to give an error. You might have to wait a little bit, maybe for a few seconds. Okay. Okay, it says failed, and then you try again, then it gives you a successful. So that failure message is just a bug in the code. So don't worry too much about that. So you say, okay, let's see if we can preview the whole thing. By the way, if you have got many component modules here, you can preview each of them individually. The same way I showed you how to view slabs. Okay, if there were others, you would simply go and edit and you can preview each of them individually. This preview here previews the entire accelerator. So if you say preview, it's gonna give you the target. All right. So this is the X-ray target here. You can close it. But let's just see if it's gonna run. Let me see if I've got my histories okay. So it does not take forever. Okay. It was 15,000. I don't know why it removed all those variables. So it put 500 hours here. All right. So um, let's just say close and save. Okay, let's try to run it and see if, all right, job is finished. All right, so our simulation can run. All right, so this is how you create a Linux. If you want to create like a real Linux, then you just have to add more component modules. I think there will be 3 or 4 more that you can add, and maybe you can use the examples first. What I want you to do today, though, is to okay, now that we've successfully done this, you have seen how we sort of create a Linux. Okay, the other technical details that are needed is just to do with how to define parameters. Let's say if you want to model a primary collimator, or if you want to model something like a flattening filter, right? How do you do it? All right, that's more of a technical aspect of it. But I think I've shown you the gist of how you model the Linux. And once you have modeled it, let's just open that folder that we've generated, okay? So we generated beam target exam, right? This is what we generated. If you open it, you can see your output, which is a phase space file, right? And the other files, they contain information like uncertainties. I believe it's either the .dat, EGS or the list has got information on statistical uncertainties and things like that. But we'll get to that. We'll get to that. That's more on the analysis stage. So let's go back to our default file, since this one really has got few histories and few particles. So it's not really going to give us much information if we analyze the output. But let's go to the default and try to analyze the output for remember we were looking at the 16 MVP, right? So now we are going to use BeamDP to analyze the output, right? So when we simulated it, we gave it 15,000 histories, but I had simulated it prior to the class with a lot of histories, right? So, and I saved it as, I believe it's, let's see. Yes, this one, EGS, what more particles. So this is something this is a simulation I did earlier on with more histories, because I know it was gonna take time to do it in class. So we're gonna analyze this. I simply renamed it so it doesn't get overwritten when I resimulate. So you should know when you rerun a simulation, your output phase space file is rewritten. So if you want to put it on the side so that maybe you can combine it with another simulation, then make sure you rename it. All right, so let's say you want to write 100 million histories, but you see 100 million is too long. You can run 50, right? And then rename your output phase space file. Then you rerun another simulation and combine the phase space files. And combining phase space files is done using the same BIMDP that we are looking at now. All right, so this is BIMDP. We want to analyze the output, this output, right? So you open it, it's going to say choose action. What do you want to do? We want to, let's say we want to look at, let's start with something simple. Okay, let's say the fluence versus position, all right? Right, you know what fluence is? The number of particles crossing a given plane, right? So we want to see how many particles are crossing a given plane relative to the position of the particles. So I'm going to click on that. Field type, let's look at, let's consider a rectangular field, all right? Number of beans, just put 200, okay? 200 is the default, right? Default. So it basically divides the if in this case we are looking at position, right? So it's going to divide that dimension, that rectangular field, into 200 equal intervals. Okay, so let's say we are just looking at from -5 to 5, which will give us like a 10 by 10 field. Okay, so from -5 to 5 in the x direction, from -5 to 5 in the y direction. Okay, so we are sort of looking at the phase space file that is within this rectangular area. And we know this area is big enough because our field is just below the target and it hasn't really diverged that much. Choose large, we're going to say none. We're not worried about that. Name of phase space file, this is what we want. So we're going to browse it, right? We're going to go to the 16 MVP, and then we're going to look at the more particles one, right? The name of file to save your output, okay? So let's just say, since we are looking at fluence, I'm just going to say flue versus position, right? Graph type, points, not histogram. Fluence, let's use the real estimated fluence, right? So let's execute it. Once you execute it, it's going to automatically plot, especially if you are working in the VirtualBox Linux. I'm not sure, maybe some of you have installed in some other systems. So I can't say if you will be able to see the plot automatically, but you will have an output file that you can plot manually, maybe in Excel or some other plotting tool. But once you say execute, or charge identified, we probably have not said what particle it is. Let's see. Yeah. We have not defined the type of particle. So let's look at photons, right? Because we are mostly interested in the bremsstrahlung, right? So we are interested in photons because we are scoring, we are analyzing the beam under the target. So let's execute and see. Right, it looks to have executed. Maybe we have to wait a bit. Let's see if it's gonna, it has to show a plot automatically. Why isn't it showing? I think it's still running. Let me try to execute again and see. It should give a plot of the fluence versus position. In sort of let me see if I put in
Sir,
everything.
I was able to get a plot because I under plot orientation, there's X and Y. I don't think he selected the field.
Oh,
Yeah.
you are right. Yeah, thanks. You're right. So you can select the orientation, so it can be in the X, right, or in the Y. So this is basically the planar orientation. So let's select X and see. All right. Yeah. So this is sort of like the fluence versus position. We have not flattened the beam or anything, right? And this is the fluence you get for this particular case. Let me see if I can change the orientation and see what kind of fluence I'll get. Okay, let's say Y. All right. Okay, it's gonna overwrite. All right, they're almost similar. They're almost similar. Um, did you what type of graph did you get? Did anyone get this type of graph, or perhaps a much more different one? Let me try to change these dimensions. Um, let me use minus 15 to 15, a much bigger field, a much bigger region. All right. Okay, so photons, 200 beams, rectangular one, photons, yeah, knowledge, and selecting the more photons. All right, point graph, fine. Let's overwrite. All right, you see? So I probably should have included a wider region. So I think I was scoring my phase space. I was scoring only the central part here, and that's why we saw like a lot of noise, because it was like a zoomed in plot of this just this region here. All right. So this looks pretty much like a profile, sort of like a DOS profile, but it's not really a DOS profile. And you can tell from the shape and dimensions that our beam from the Linac head was collimated to produce a 10 by 10 field. You can see it ranges from -5 to 5. Okay, this area is basically like a penumbra of the profile. So the actual field is probably a 10 by 10 field, right? Ranging from -5 to 5 in the X. It's probably the same in the Y as well. We can verify that. Okay, this was the Y. Let's go to the X. It's probably gonna give the same type of fluence. Right. So what happened? All right, so it's similar. Okay, so this is a 10 by 10 field, and I'm sure you can verify that as well. If you go to the beam itself, you'll see it's a 10 by 10. I'll quickly show you that now. All right, I'll just go back to the Linux itself and show you, because I didn't make this Linux. So all right, so if you go to jaws, which shape the beam, then you see this is a secondary collimator set to produce a 10 by 10 field at 100 centimeter SSD. All right, so our affluence makes sense. All right, because it's sort of high within the field size, and then drops to almost to zero beyond the field edges. All right, so that makes sense. You can also, if you want, do other things. You can look at spectral distribution, for example. Okay, I'm just going to show you spectral distribution. And then I'll show you how to combine two phase space files. Okay, again, photons. Let's just say minus 15 to 15. I think it's safe. And that's the default. Minus 15 to 15, minus 15 to 15 in both directions. All right. And beams, we're just going to put the default, which is 200. You can't put more than that unless you go to the source code itself and modify it and recompile it. Otherwise, if you go beyond 200, it's not going to run. Minimum energy, 0. That was for a 16 MV incident electron beam. So we're just going to say 16. That would be the maximum energy of the photons produced. Knowledge, same phase space file. Now this is the spectral distribution. All right. Point graph, estimated fluence. Right. Let's execute and see. So this would be the spectrum of the beam. All right. As you can see, this looks like a typical spectrum you might have seen in one of the radiation physics or oncology or imaging courses. By the way, does anyone have any idea what this peak is about? What do you think that peak represents? Actually, I think I'm just gonna include it as part of like a questions. But if anyone wants to try, you can. And by the way, when you move your mouse cursor in this figure, it gives you the coordinates of the X and Y. So you can place it anywhere and it will tell you the fluence and the energy. So for this peak here, if you place it right here, it will tell you the X or the energy is about 0.517. The fluence is about 1.5 to the negative 6. So does it really ring a bell? What is the significance of 0.551 MeV? How is it produced? I think it rings a bell, right? 0.511 MeV sounds familiar. All right, but I'm gonna include as part of the exercise. So you can do several plots. I'm not gonna go through each and every one of those, but you can just plot each and every one of these. You can do a scatter plot, all right, which basically gives you it tracks each and every particle and then it shows it as a dot. So for example, maybe I might be able to show you this. Let's do a scatter plot. Let's change the phase space file and use the file with more sparsely scattered particles, because this one was run with a lot of particles. So it's just going to show you a black a region because there's just so many particles. It ends up just being a solid graph. So let me show you a more sparsely distributed phase space. I think this is the one that we just ran. All right. So photons, minus 15 to 15, everything the same. I'm just going to say, oh, wait, maximum number of particles. Well, we did put 15,000, right? But I think if you set it to 0 or less than 0, then it's going to use the total number of particles in the file according to this. So let's just say 0, and it's going to take all of them. And here we are plotting the scatter. So this is the name of the file that's going to be output into this folder. In case you want to use a third-party software to plot, all right? Such as if you want to plot different profiles on the same graph, you can output them into a file, and then you can use Excel or whatever to combine them into one axis. You can do that also with XMGrace, but you might need a little bit of Googling. Anyway, let's execute scatter minimum and maximum energies. Oh no, you can't do this. Minimum energy is 0. Maximum energy is 16. So you must be careful when you change from one let's one analysis to the next. Okay, it has a habit of copying previous inputs and placing them at the wrong place. Okay, you saw it with the EGSnrc input files, that when I tried to save incorrectly, it distorted my input data. So make sure you check everything before you execute. Okay, so everything looks fine. Let's execute and see. This would be the scatter plot. So this shows all the particles on a plane. All right, so just below the target. This is the distribution of particles. Again, you can see this is roughly from -5 to 5 within the solid region. And of course, you do have scattered photons all over. But the field size corresponds to this scatter plot, right, which is -5 to 5 in the X, -5 to 5 in the Y. So this is a plane, as if you are looking through the target, or as if you are looking through the exit window of electrons and looking onto the target. This would be the distribution of photons just below the target. All right. Now I'm going to show you how to combine two phase space files. So in which case would you want to do that? For those of you maybe who are not interested in doing parallel processing, which is basically used to sort of divide one simulation into several. All right. So for example, this one that I did, I used about, I believe it was 100 million histories. All right. And maybe your laptop is not that good, or you don't want to run one long simulation. You can divide it into 3 maybe. You can run the first maybe with 30 million, you get your output, you rename it. Then you run another one, you get your output, you rename it. The reason you rename is because you don't want to overwrite. Okay, so let's say now you've got 3 phase space files, right, from the same simulation. But by the way, there's one very important thing. All right, when you do that, make sure you change this thing here. Let me just quickly show you this because it's important. You change the what we call seeds. All right, we call them random number seeds. I thought I had an accelerator open. All right, so let's say you have run your simulation, right? You have collected your phase space and renamed it so that it does not get overwritten, and then you rerun. Before you rerun, you change these random number seeds. So that's this initial RNG means random number generator seeds. The reason you change this is because Monte Carlo itself is based on random numbers. Right? For those of you who have done computer science or some type of programming using Monte Carlo uses random numbers. Okay, so it generates numbers between 31 and 77 in this case, and then it uses them to do this sort of probabilistic simulation. So before you rerun the same simulation, change these. So you might change it to, it gives you the limits of these numbers, okay? As long as it's between 31,298 and 30,000. So you've got a lot of flexibility. You can just say maybe 5,006. This one you can say 7,760. It doesn't matter really, as long as you change those numbers. Because if you don't, you might just reproduce the same phase space file, okay? Once you do that, you save and then you rerun, okay? Which means you're gonna get a phase space file. And now you've got 2 phase space files of the same simulation, which you are going to combine. So if you run the first simulation with 30 million, the second one with 30 million, it's as if you've run a one log simulation with 60 million histories, okay? So that's one of the reasons why you might need to combine 2 phase space files. Now, how do you combine those? All right, you come on your BIM-DP, right? So BIM-DP is going to, you come back here on the main interface, you go and combine 2 phase space into 1. All right, so you browse the first one and the second one separately. All right, so Let's do it. And one thing you should know is that the data is merged into the second one. All right. So I'm gonna browse the first one here, right? And then I'm gonna browse the second one here. So the second one is the one into which the output is is produced. So if I say execute, it means this one is going to be overwritten and replaced with the combined data, right? You understand? All right, so the first one is left alone. The second one is overwritten and replaced with the combined output. So you execute it. Sometimes it might take some time depending on the size of your phase space file. So just be patient and wait for it to run. All right. So this one seems to have run, and you can actually look at the information here. It gives you information of the first phase space file, which had 200 and for some strange reason, if I scroll, it takes me back down. Anyway, the first phase space file is about 262. For some reason, I'm scrolling and it's going back to I'm not sure, but anyway, it gives you the number of particles of each phase space file, the minimum energy, maximum energy, and then it gives you the details of the merged phase space file, right? So now we have got a new phase space file with this name, right? So that's how it works. Is there anything else in simulating the beam and analyzing it? I think that's it. Basically, the different ways, the things we can change would be the types of sources. All right. So here we chose a parallel beam from the front. There are other types of beams that you can use, but we are not really using them because we want to focus more on how we are going to calculate DOS eventually. So there are other different types of sources, all right? Like a rectangular beam from the front, parallel circular beam from the side, okay? You can have an elliptical Gaussian beam, full phase space data. You have different types of sources that you can use, but for a linear accelerator, it's simply a narrow electron beam that hits a target. Okay, so this is good enough for us. If you are, however, simulating something like an X-ray tube, right? Like either diagnostic or therapeutic. Remember, a linear accelerator has got a transmission target. So in other words, the beam simply comes and passes through the target. A reflection target, on the other hand, that is used for diagnostic X-ray tubes, would require a beam that comes from the side, impinges onto the target, and then is reflected towards the patient, right? Remember, the X-ray tube, there's an anode angle. So the electrons hit the anode at an angle, and the X-rays are produced at an angle and directed towards the patient. But we are not really simulating X-ray tubes. For those who are interested, I can give you an input file for an X-ray tube, and then maybe you can simulate it and preview it and other things. But we are mostly focused on Linux because that's the equipment we have, right? So once you simulate your beam and you've got your output, remember, like I said, for a full Linux simulation, in this case, the phase space file would be scored just below this component module, right? 1, 2, 3, 4, 5, 6, 7. This one is 7 component modules, right? So when you define your scoring plane, right? On scoring plane, you say one scoring plane, okay? But it's beneath or below component module number 7, okay? Because we have 7 of them. So that's what you do, okay? To find it as a square, that's fine. So you can ignore the zones. It's not really a big deal, but make sure you are scoring your phase space file at the right position. because you see some people, they score the phase space file at two different positions. For example, they'll score it just below a target to model Bremsstrahlung or photon production, right? And then they model the linear accelerator in two parts. The first part only models photon production in the target, and then the second part would model the collimation of the beam, right? The flattening and the collimation of the beam through the other components. So you might see that sometimes there are two stages of simulating the beam. I'll give you an example. I think I do have an illustration here. This is part of a research I published. You can model this was an X-ray tube, by the way. So the beam is produced and you can model the beam production through a filter. Remember, there's a filter in an X-ray tube, right? Aluminium usually, or copper. And then you score your phase space. And then you can now model the second part of the machine using this phase space file as input. All right. And then you collimate it through whether it's a circular or a square. For X-ray tubes, usually it's a circular collimation. And then you then score again your beam below the beam collimation system, okay, or just after the beam exits your machine, right? And then for the second part, in this case, I was modeling a homogeneous phantom and also some heterogeneous phantoms, with one with lung, the other one with bone. So you can then simulate those in the phantom using those XYZ, all right? So this is pretty much the same geometry we are using here, except that we are using this as the radiation unit, and our phantom, which would either be a water tank like this, or a real phantom, patient phantom, right, based on CT data. All right. So same geometry, just different materials. Is it making sense? I want to see some comments in the chat. I know it's probably quite a lot of material, but once you get to the practical aspect of it, then you see that it's just a matter of looking at the examples. All right, you have got 3 examples. So for the Linux that are shown, I just gave you this one as an example. There's also the one for electrons, right? So this one does not have a target. Remember, for electrons and photons, you've got different components. So this is for electrons. We did one for photons. I'm not sure what these other 2 are for, but you can analyze them if you want. The other ones are my personal input files. Now let's assume you have modeled your linear accelerator or X-ray tube or whatever. Then now you want to model the DOS in the phantom. So let's quickly look at DOS XYZ and look at how it models the DOS. All right. So I've already given you a background here, theoretical background. There are some manuals that are used for BeamNRC and DOS XYZ. All right. I will share them with you in case you want some extra data. And I'll share with you as well my MSc dissertation, in case maybe you just want to see what I did and how you use Monte Carlo in more detail. I'll share with you. I did do the same thing for my PhD, and if you're interested, I can share with you as well. Let me just see. There it is. Let me just see if I can take you to. Nah, this one would be too much. This one would be kind of too much because it takes a real treatment plan, and then there's a bunch of conversions, and so this is like, but anyway, just to let you know what you can do, you can actually take data from a treatment planning system, and then of course there's some conversions because the coordinate systems are not always compatible. So there's a coordinate system conversion, file format conversion to make everything compatible with EGSnrc, and then you can simulate. So I believe here I did 3D conformal for the bladder, for the esophagus, and for the cervix. And so you can do some Monte Carlo simulations and come up with some dose distributions. I believe in this case, I did some gamma analysis of comparing treatment planning system versus Monte Carlo. Okay. And you can do gamma analysis or TVH analysis. You can do isodose comparisons and things like that. But yeah, TVH as well if you want. And you can do some dose statistics. You can compare things like what's the minimum dose, maximum dose, what's the dose difference. Yeah, but I don't think you need all of this right now. The only thing you need is to know how to model the dose in a phantom. I don't think we will have patient data, but maybe if I browse through my old files, I might give you just a patient file that is already so basically CT slices that were already combined into a single EGS compatible file. And then maybe you can model a beam. And the beam directions can be changed in DOS XYZ. In other words, the gantry angles. So let's look at DOS XYZ. All right. Naturally, when you do DOS XYZ, let me try to open an input file. All right, let me load an input file here. So I'll share the recording for this class. So let's just quickly do DOS XYZ, and then you can try to I'll give you something to do, and you can then let me know if you are having success. And then in our next class, we'll look at how we can analyze the dose distribution that we get from dose XYZ. So I want to see if you are able to simulate at least an example, an input file that is already existing, right? You're able to compile it, run it, analyze phase space parameters like fluence, scatter, spectrum, and things like that, and plot and save the file, and put it in a document, and you're able to then transport that phase space file into the phantom and calculate the dose. And then in the next class, we'll look at analyzing the dose itself, the 3D DOS file that you get. So let's try to load the input file. In this case here, let me just see if there are examples that we can use. But if we are not successful here, what we'll do is 16 MVP water. Okay, let's see. This looks like the same. Okay, this uses a phase space file. All right. Let's see if we can be successful with this one. All right. If I'm not mistaken, okay, let's see. All right. So once you load, it's going to give you a pop-up. Okay, let me close this. It's going to give you a pop-up window with all the input parameters that you can edit. Okay, just like a number of histories, like the incident particle. Like, what is your source basically? Is your source the phase space file that you just simulated from BeamNRC, or are you just defining your source from scratch? All right. We would want to probably do both, but let's see which one, because I haven't done this prior to the class. So let's see. In this case, our phantom is from non-CT data. All right. So it's not an actual computed tomography data. It's a phantom that we are going to define. So if it's a non-CT data, if you say from CT data, it's going to ask you to browse for the actual phantom. But since we are defining it, you just have to click on here, define using, right? And I believe this is already done for us. Okay. So we are not defining voxels individually, okay? We are defining them as groups. So we have got 3 groups in the X direction, Y direction, and Z direction, okay? So let's see in the X, okay? In the X direction, in this case, the minimum boundary, so this basically defines the size of your phantom. That's what we're doing here, okay? So our phantom is from minus 10,25. I believe the 0.25 is just put there for to make sure that our 10 by 10 field is not too big for the phantom. But so from minus 10,25, and each voxel is 0.5 centimeters thick. And if we put 4 to 1 of them, then our maximum would be 10,25. All right, so our phantom basically ranges from minus 10,25 to 10,25, okay, in the X dimension, each voxel being 0.5 centimeters thick, and we've got 41 of those. So basically here, if you say minus 10,25 plus 0.5 times 41, you get plus 10,25. All right. So this is the width of the phantom in the X dimension. Same thing in the Y is from minus 10,25, same width of each voxel, same number of voxels. So it means the maximum boundary of the phantom is going to be 10,25 centimeters, all right? So X and Y we normally define from negative to positive, with the midpoint being at 0. We do that because we want our beam central axis to coincide with the 0 or with the center of the phantom. So we just define it as centralized at the 0 mark. The Z-axis, on the other hand, it starts from 0, okay? So we assume the surface of the phantom is Z equal to 0, okay? And then it goes all the way. In this case, you've got the same thickness of voxels, and we've got 80. So it means in this case, the depth of the phantom, or the height, is 40 centimeters, right? Because it begins at 0. So it's basically 0 plus 0.5 times 80. So the maximum, your phantom would go all the way up to 40 centimeters, all right? So we know what our phantom is. What about the medium? Okay, what is the medium in the phantom, right? In this case, there's only water and air, all right? So what you do here is when you input here, you can just say 2 if you have got 2 medium only, all right? And then you define them. Okay, you browse them, so you click here, right? And then it gives you the actual medium, okay, water, or you browse here, air, all right? In terms of the voxels, you want to specify, okay, which voxels are consisting of water, which ones are consisting of air, right? We know that in actuality, we've got different media, but this is a simplified model. So of course, you put the density of water is 1, density of air is 0.0012. If you're not sure about the density of air, you can just check in the PEX4 file, all right? So in the PEX4 file, you do have, they write it as raw. Okay, let me just show it to you so that you don't analysis spec. PEX4 is here. I just want to show you, let's say you want to use a material that you're not sure which density it is. So let's say it's ICRP bond. Okay, so let's say we're modeling bond. You look at raw, density is represented by raw. So this will be the density of the material. But for most materials, it will be usually just water, air, maybe, and bond. Okay, so I'm gonna give you some crazy materials. Unless you want to expand, maybe we can expand to a metallic object to see how it can disturb the beam. But so in this particular case, we've defined our phantom to be a cubic phantom, and the first layer of the phantom from voxel 1. Okay, so in the X dimension, all the voxels from 1 to 41. In the Y dimension, all the voxels. And in terms of depth, from voxel 1 up to the middle of the phantom, which is voxel 40, they consist of water of density 1. And then below that or beneath that, all the voxels from voxel 4 to 1 in depth to the last one consist of air, right? So that is sort of like our phantom here. Okay. And of course, you can visually see your phantom, but that's something I will do next time, right? Now that you have defined your phantom, you can just say output xphen file. The reason why it's a good idea to do this is because you want to visualize the file when you do DOS analysis, right? Remember, when you do ISODOS, when you let's say when you look at ISODOS lines, or when you look at the treatment planning system, it gives you the DOS overlaid on top of the actual patient phantom or patient CT data. So you want to see your DOS superimposed on top of this phantom. So that's why we want to output it, because we generated it within the software. So we want it to be output as a file so that later on we can overlay our DOS on top of it to see the spatial location of whether it's a hotspot or whether it's a DOS gradient or whatever. All right. So in terms of the beam that is impinging onto the phantom, so what we were doing here was to define our phantom. If it was a patient CT, you just click here and you browse it if you have the file, and you won't have to do all that to input all those parameters. And in terms of cutoff energies, we'll just leave the defaults as they are, right? And number of histories, you can modify them based on the speed of your computer. Maximum CPU time, I said 500 is a good one. And the seeds, you can just leave the default ones, right? You can leave all of this as it is. How far less is usually used if you have got a homogeneous phantom, right? You can switch it on if your phantom is homogeneous, right? Which means a single medium. But in most cases, that's not the case. So switch it off unless you've got a homogeneous phantom. All right. In terms of these other parameters, let's just leave them as default. Okay, don't worry about this for now. What I just want to show you is the source itself. Okay, so we are taking the source type as a full phase space source file. All right, so I'll just show you. Right, this is our source. Remember, we already generated our beam, right? Our phase space file is literally our source. Okay. Now, coordinates of the isocenter, you just say 0, 0, 0. Our beam is incident onto the isocenter of those coordinates. So those are the coordinates of the isocenter, right? Those may be different if you are dealing with a real patient, okay? And of course, that information you get it from the treatment planning system, but we are not doing that. So we're just sticking to 0, 0, 0. These angles here have to do with the gantry angle, the collimator angle. And okay, so the collimator angle is here. And if you are rotating the source, for example, then you might put a certain angle, but usually our source is not rotated. So just stick to these angles if your beam is incident perpendicularly onto the phantom, right? However, on distance from source to isocenter now, this depends on the distance from the source to the phase space file. Now, because now remember, there's the distance from the source with the actual source, which is the X-ray target, to the phase space file, right? And where you scored your phase space file. Now, this distance is the distance from the phase space file to your phantom, whether it's on the surface of the phantom for SSD, right? So this is basically 100 minus distance from source to phase space file. Okay, so when we simulated our linear accelerator, you can go onto the beam NRC and see what is the distance from the source to the actual scoring plane. Okay, I think I can leave you to look at that. It's something you can figure out. And then you can just deduct from 100. If your aim is to treat at 100 centimeter SSD. So this would be 50 centimeters. If your distance from source to isocenter to phase space, sorry, was 50. Then from phase space to your target or to the source, to the surface, sorry, would be 50 centimeters. That's the only thing you need to change here, just this distance. The other parameters, leave them as they are, unless you want to change the geometry of your source, okay? And in terms of the phase space file itself, you can just browse it here. Let's try to browse it, okay? So if you want to go back, all right, so because here we are in the wrong directory, so what you want is to click these dots. It takes you back. I think we want to click again until we get to the beam, which is the linear accelerator, which is the 16. And then we browse the more particles space file. Okay. And yeah, you just say okay. All right, leave the other parameters as they are, and you can close. Don't forget to save your parameters. Let me remove this, probably gonna confuse some people. That was for EGSnrc. So save, and let's compile first. I hope we are not going to have an error. We might have an error initially for compilation, but I hope it runs. So let's see. Let's see. Okay, it looks like it's successful. All right, let's see. By the way, if you want to edit the parameters, you can just say File, Edit Parameters. It will give you this whole window here, the one that pops up when you open a new input file, and you can edit your history. So let's just put 15,000 maybe, yeah, and close. Don't forget to save every time you don't really have to compile if you change something like histories, but if you change maybe the geometry of the actual simulation, or you change some major things, then it's always a good idea to compile anyways. So let's try to run it. All right, I suspected it's going to fail. It probably has to do with the input parameters themselves. All right, but what should happen is it should run similar to EGSnrc. Rather, let me give you it's difficult for me to sort of diagnose or to see where the error is coming from, because this is just an example input file. There's probably some clashes between our output in phase space and the way this thing was created. So what I'll do here is remember this. In this particular case, we are importing the phase space file as the source. I'm going to show you a different way, in which you define the source yourself. So let me just close this and reopen .xyz. I do have an input file that I created myself. So let's load that one. I believe it's water test, maybe. I think it's water test. All right. I just want to see if this one runs. Okay, then I'll these are too many histories. Let me just say 15,000. I just want to see if this one can run. Let me compile it first. And then I'll run it. But most likely we are going to use a phase space input. This file is different. This simulation is different because I used a parallel beam from the front. So it's almost like I am creating my own source here. Okay. So this was an electron parallel beam from the front in which I just input the parameters. Okay. So the beam had these dimensions in terms of length and width. And in terms of the angle of incidence, okay, it was 90. We must be careful here because sometimes it will say cosine, but in this case, it's just saying degrees, okay? So it's 90 degrees relative to the surface. So 90 with X, 90 with Y, and 0 with Z, okay? And these are simply this is simply the width and the length of the beam, okay? Let's make it a photon beam, right? So I've got a photon beam of those dimensions incident perpendicularly onto a phantom that I have defined similar to what I showed you earlier on. Okay, nothing different here. This is just a much smaller phantom, which is from 0 to 10 centimeters. It's like a 10 by 10 by 10 cube with a single media. In this case, it's just water. All right. So I have not really defined the voxels because it's just going to be assumed to be water. So you don't have to really define the voxels. But if you've got more than one media, you need to specify which media has got which voxels or which voxels contain which media. All right. So again, don't forget to output for visualization. All right. So this is what I created, and I'm just gonna save. Did I run it? Let's run it. Okay, you see, it's running pretty fast because of the 15,000 histories that I put. Okay, but what I would say is for beam NRC, start with I would say 10,000 histories, and then move on to oof. So in my case, how many did I use, by the way? I just wanna I probably changed it. What I would say to you is this, maybe this is going to be part of something you will do on your own. Try to load that 16 MVP, that's what beam NRC, and try to simulate it with 10 million histories, 10 million histories, okay? See how long it takes. If you wait for more than 30 minutes and not a single batch has run, remember they are divided into 10. If you wait for more than 30 minutes and not a single batch has run, then try to reduce your histories a little bit. Okay, you don't want to wait forever. You want to do that once you are doing like a final simulation. If you want to like present your results, then you can put as many histories as you want, and then you can wait. Right. So I would say start with 10 million, see how long it takes, and increase them until you get to, I would say, 100 million. Okay, for 100 million, you might need to leave your computer running when you go to sleep. You see the results in the morning. Just make sure your computer is not crashed based on the number of histories you put. So I hope when you installed your virtual box, you put the right amount of resources. Okay, so if your computer is 4 gig RAM, don't put 3 gig RAM to your virtual system, while you know your host system is using more than 1 gig. So distribute your resources wisely. Otherwise, stick to a little bit of fewer histories, and then you can combine your phase space files like I showed you. So these are things you would do on your own because every computer is different, and they will run with different times, even for the same number of histories. So what I want you to do now, since we had a failed message for importing a phase space file, I want you to try to modify the let's see, what I'll do is I will I'll send you, let's see if we've got default input files that you can use. And you can just modify and save as. So what you can do here is, let's say you are working with this, you can say file, save as, right? Because you really don't want to change the examples that come with the software. So make sure you don't really edit them. So when you open them, the first thing you do is to save input parameters as, and then you can create your own linear accelerator or .xyz input file. Okay. Don't edit the original files because you might need them later for reference. When I ask you to create something from scratch, you need to copy and see, okay, this is what it looks. If you want to model this shape, you do it like this. Okay, so first thing, you open a file, save as, and then you give it out a title, and then you work with the copy, right? So for .xyz, I want you to open one of the original files and then try to import the face space file from EGSnrc and see if you can run. I have not done it like a diagnostic test to see why that other one failed to run, but that's something I want you to do. All right, so let me summarize because I think I've spoken enough today, and I think you will have enough to deal with until next Monday. So what I will do is I will email you my MSc dissertation, just so you, if you missed something when I was introducing the chapter and maybe the whole workflow or what happens from the moment you simulate a Linux to the moment you get a DOS distribution, right? And we did not cover how you display the DOS, okay, because that's something we'll do next week. So but this document will have everything. The only difference is this interface will be a little bit different. In this case, I used what we call MC Show, but we will use what we call DOS XYZ Show. It's a very similar user interface. But we'll do that next time. Once we have got some progress in simulating the treatment unit and the DOS in the Phantom. So what you have to do is to first of all simulate or resimulate these. Let me just open them up. All right, the one we've done, try to simulate with more histories, right? You can try 10, 15, maybe I would say up to 50 million would be very good. Once you know you have played around with the user interface, try to run 50 million, and it will probably take 12 hours or 6 hours, because I ran 100 with my computer and I think it was around 12, 13 hours. So it was overnight. But that will be different for everyone. So try that, and then try to open this one for electrons that we haven't done. Try to see if you can compile and run it. Remember, you might have to compile 2 times. If you get a fail, compile again, get a success, then you can run it. If you successfully get your EGSnrc to run, then you get your face space output, right? Then you got your .xyz, right? And then once you do that, you try to open an existing input file. For example, you can load, let me see in examples here. Any of these, okay? So let's just say, let's look at this one with a face space input, right? Load it with the 700 ICRIU PEX 4. Once you do that, try to see if you can run it. If not, try to see which parameter isn't making sense, because I haven't really done that. Another thing I'm suspecting might be a problem is the PEGs 4. All right. You might need to change it to the 5-to-1 ICRIU. I'm not entirely sure. Okay, this one won't work. Let's see. Oh, okay, it's saying I should go to local area. Okay, let's do this. Let me try to run it again. If it doesn't run, it's probably something to do with the parameters here. All right. If you are not able to get it to work, I will do a diagnosis. But I encourage that you you do it so that you get familiar with it. You know, the more you click and see things, the more you get familiar with, oh, this parameter means this one means that. And there's also a user manual. I'm going to email, or I'm going to upload it on my e-learning. I'm going to upload the manuals and also the other documents. All right. If you're not able to get any DOS XYZ input file running, let me know and I'll give you a sample that runs like the one that I just ran here. All right. So another thing is to use BIMDP, right? I've already shown you how. If you get your phase space file, try to use BIMDP and do all these operations here. All right. So once you create your phase space file for both Linux, right? Remember I said for the electrons, for the Tane MV, this one, and the photons, try to do all these operations here. All right. Do each and every one of them individually. It's quite straightforward. And store your output. Your output is just going to be in the same Linux folder here, if you're dealing with this one, for example. So do that, and I will write down sort of the things I want you to do. But for now, I want to make sure that you can use the software. You can run the example input files. You can edit certain parameters. You can preview the accelerator. You can create a phase space file and you can analyze it in BIMDP, and you can import it in DOS XYZ and calculate DOS in a cube of water. All right. So if you can do that, then you will be good. So I think I've spoken enough. Maybe if there are questions, I can take questions now. Maybe you can let me know. Have you been following? I tried to summarize my 2 years of masters in 2 hours, but I hope it's not a lot because we're only dealing with the basic stuff of calculating DOS in water. We won't use any CT data because that will require at least 6 sessions. So I'm not gonna trouble you with that. We're simply calculating DOS in water. And as we go, we will edit our water phantom to include a lung and a bone and maybe a metallic object in there, just to calculate the dose perturbation in the presence of inhomogeneities. So if you've been following, let me know in the chat, or you can unmute yourself before I otherwise for today I think I've said what I wanted you to know. For those who have not been able to attend, I'm not sure how many there are. These lectures are recorded. These sessions are recorded. So today I've got 2 recordings. The first one is a bit shorter, which was the introductory lecture on the software, and the second one would be quite long. I believe it's I don't know, more than an hour, where I was showing you how to use this Monte Carlo thing. But is it making sense? Or where were you lost? If you were lost, let me know where you were lost so I can try to clarify.
So I followed pretty well. It's just the only thing is that in the beam underscore EX16 MVP folder, the one that's on the screen right now, yeah, so I'm not able to access EX16 MPV more part. I'm not able to see, yeah, the more part
Yep.
file. I'm not able to
More,
access. Mm.
more part, which one is it?
Mm, It's third row, the fourth file on the third row. Yeah, that one.
This
Yeah.
one.
Yeah,
Oh
I'm
no,
not
this is something I created. Okay, so what I did, I simulated the normal Linux, and then I renamed it.
okay.
I renamed it because I didn't want it to be overwritten when I do illustrations in class. But if you see, there are two outputs. There's this one, which is the one you should have.
Yes, I
This
have
is
that
this.
one.
Yeah,
Yeah.
yeah, yeah. This is the one I simulated on my own. I think a week ago. And if you can check on the bottom right corner, it's 841 megabytes. Simply because I ran 100 million histories, so it's almost a gig in terms of size. So I renamed it because I wanted you to see smooth curves when I plot, spectral distribution and things like that in BeamGP. So
Yeah,
when I,
so
yeah, mhm,
when I since I didn't have that file, when I plotted my own one, remember we had to use either X or Y, I did not get a smooth curve. I had a lot of noise because it
yeah,
was not the file I was using. So that would account for the noise that I got on my end. Yeah.
yes, yes, you will get a lot of noise if you use few histories. So that's why I'm saying try to run with fewer histories and try to analyze your spectrum here or whatever. And then if you see there's a lot of noise, rerun your beam with a bit more histories, maybe double them, triple, and see until you get sort of like a smooth profile. In terms
Yeah.
of the dimensions here, just use the default, like from -15 to 15, so that you know your beam is within that zone. So when you define, for example, here, just let's see, let's say it's a rectangle. Just use -15 to 15, -15 to 15. Yeah. So yeah,
Yeah.
that will account for the noise. The noise is you're gonna have a lot of zigzag sort of lines. If you saw the graph I plotted at first when I sort of zoomed in, that looked noisy, but it wasn't really that. It was because I took like a small region and I zoomed it in.
I think you took
Um,
5 and -5 and you put it.
yeah,
And when we used the 15 and the -15, it was more of like it zoomed out. So you was able to
yeah.
see the curve. Yeah.
Yes, yes. So make sure your dimensions would encompass the whole field. Okay, so in this case, it was a 10 by 10. So -15 to 15 would cover pretty much the field accurately. Or you can use -12 to 12. You don't need to make it that big, but you will need prerequisite, or let me say you would need to have the knowledge of how big your field size is. So to know how big your field size is, you would either have to go to BeamNRC and click on the JAWS, like the beam collimation system. There is a description of, for example, it's written beam collimated to 10 by 10 at 100 SSD. So you know your beam is 10 by 10, and you're gonna open up a wide enough region to score your to analyze your beam. Or you can simply do by trial and error. Just use a 15 by 15 and you will see where your penumbra begins, like sort of, those beam edges. It should be clear, especially for regular fields. I think those are some of the things you can play around with um, to see. And also make sure you look at that peak on the spectrum and know what it represents. All right, thanks for the question. Is there anyone else with a question? Have you all been able to install, and so you are able to open up the GUIs like I was doing? And you've got the EGS home and EGSnrc and all the spec module folder. You've got the linear accelerator folders and PEGs4 file and the DOS-XYZ. By the way, DOS-XYZ, I haven't shown you the folder. Let me just show you. Because I think I forgot. The DOS-XYZ, you go to your home, same folder with the linear accelerators. Okay, go to DOS-XYZ. All right. When you simulate something successfully, you're gonna have a 3D DOS like this one. Okay, so same file name with the 3D DOS file. All right. I think I did plot some things before, but some of the things didn't make sense because I was still trying to okay, this was, let me see. These were DOS profiles that I plotted, all right, for a water phantom in the X and in the Y. I used I believe it was DOS XYZ show. I'm not sure. But don't worry about this for now. But as you can see, you can get your nice DOS profiles in DOS XYZ. But I think it will be too much to give you now. I think we still have 2 more sessions, I believe, 2 or 3, maybe 2. So most of the work, as you can see, would be independent work. Maybe not so much independent, but you playing around with the interface to get used to some of the parameters that we didn't get time to look at. But I did highlight the most important parameters. So most of the work here will be just you editing input parameters, right? So for example, in EGSnrc, by the way, you can't load an input file and just edit on, so let's say you have opened this 16 MVP, right? The only way you can edit is if you are modeling the same make of a Linux. In other words, a Linux with the same components in that order, okay? So you can't really edit. So let's say you can't move jaws up here and move the chamber down here. Once you create these, they are there. All right. So when you create a new accelerator, you're going to have to create it from scratch like I did. You specify a new accelerator. Okay. So, however, I want you to get used to editing these input files. All right. So, for example, if I tell you the flattening filter it's not made out of okay, this one had many cons. Let's look at a little bit at a simpler component. Okay, so let's say this one, which is tungsten target. Let's say I tell you the target is made of, I don't know, rhenium and tungsten. Let's say it's an alloy, 10% rhenium. And so what you're gonna have to do in that case is to create that material using EGS GUI. So this is something we'll do next time. Next time we'll look at how to create a custom material, and then you simply append it to the existing Apex4 data, as well as visualizing. We'll start with DOS XYZ and extracting PDDs and other things. All right. So for now, most of the time you should spend it on BeamNRC, and on DOS XYZ, try to load an existing input file, edit it, and try to import your phase space as the source and see if you can simulate the DOS. If you can get the 3D DOS file, then that will be, you would have done the bulk of the work. Most of the work will be on editing and in different phantoms, different media, different tungsten material, or because most of the components in a Linux don't change. Actually, nothing changes, but sometimes you do put accessories on the Linux which can modify the beam, effective energy, and things like that. But we can edit a few things and analyze the output. So if you have any questions of what you want to do, you now know what you have to do, right? Try to see if you can load those 2 Linux electrons and photons, analyze the beam with beam DP, plot them, right? And save the files as images. And maybe you can share with me in the next class. I would write an exercise. This is not yet an exercise. This is just you getting to know how the software works. So in the exercise, I'll just write things you need to do, like, okay, step 1, do this. Step 2, do this. Up to the end where you display the DOS distribution. and maybe make a conclusion about the DOS or describe why the DOS looks like that. The DOS looks like that. For example, if there is a bone in the medium and the DOS decreases or increases on the interface or whatever. Right. All right. Any other question? Otherwise, I think we have done enough today. My voice is kind of messed up, but if you have any questions, feel free to ask me now, or you can email me, or if you have a problem whilst doing your simulations, you can WhatsApp me or email me. I did say you should all have AnyDesk installed. It's compatible with Mac and Windows and Linux. So that's for me to be able to control your computer from here if I want to show you something. We can, that's for remote access. So, all right, if there are no questions, I think we'll call it a good night. And yeah, happy EGSnrc week. I will, for those who haven't attended, I will make some arrangements if we need to. So, good night, everyone. We dismissed a bit early. Oh, no, it's not actually a bit early because we started at 4. Oh, I can't believe it. Good night.